And so this is one of the pages where I keep logging my research articles, and I'd put it in chat for you to
Okay, okay.
refer at a later point of time. And so what we are seeing over here is I have Anaconda, Android development, artificial intelligence, cloud, cybersecurity, databases, Databricks, deep learning, Flask. Flask we would need in case we need to deploy our machine learning models. And then there is GitHub is required when we need to check in our source code. Hadoop and Spark is different game. Now there is this machine learning linear regression theory and improvements over OLS. Linear regression falls under a class of machine learning problems. So when you have a linear regression, what do you understand by it? You have some data points in two-dimensional space. If we are talking about two-dimensional space, it is like you have some data points and you are trying to predict the value, the target value y for a known value of x. And the way to do it is that you draw a straight line to get an approximation of how y is related to x. Now, when you do that, you have ordinary least squares regression algorithm, which is available by most packages like we discussed before, scikit-learn, SciPy, NumPy, Pandas, all of that. Now there is when we come to any machine learning model or there comes this concept of degrees of freedom. So degrees of freedom is that suppose your data set has only 2 points, and how many data points, if you draw your model in linear regression, your model is a straight line, right? Your model is
Correct. It is y equals to mx plus c. Yeah.
yeah. If y equals to mx plus c, then what do you need to know to get a data point? If you have let's say you know the value of c and you know the value of m, then you can easily figure out what the equation is, what your model is, what your model which line is representing your model the best. So the degrees of
Okay.
freedom in case of a line is 2. So a line has 2 degrees of freedom. Having 2 degrees of freedom means that there are 2 independent parameters that uniquely identify a line as
Means x-axis and y-axis. Yes.
not x-axis and y-axis, the slope and the where it cuts the y-axis.
Okay.
So
Right. C and the m.
C and the M, yeah, I'd show it in paint, or you shall I show it in paint, or it's
No, no, no.
okay?
It is fine. I got it. I got it. Yes, yes, yes.
Like if this is the C,
This is a C, correct. Where it is
yeah,
cutting. Yeah.
yeah, and
M
this
is that whatever the angle. Yeah.
and this angle is theta like M. Okay, okay. Then regression. What we basically do is we try to get just the what we try to do is that we have a function to learn, and we that function is our target value, and that maps to the x. That x we are trying to learn y with respect to x. Now what do we call this? We call this a function, that y is a function of x, and the way to represent that is given in these equations. Like you would mostly see, you have a yi and you have an f of xi. That means f of xi is what your model is giving you, and yi is what you actually have. So absolute error is difference between the data points that you have, yi's that you have, and f of xi's that you calculate. Now, when squared error, the equation for squared error is this, that you sum the squares of differences of all the errors. What is an error term? Before we
Mhm.
do a further, oh, 1 second, I need to take a bit of.
Does it means for a particular coordinate yi is the your this one that y-axis distance and xi is the x-axis distance?
Hmm. So 1 second, 1 second. I'll explain in this
Hmm.
picture only. In this picture, I'll copy it, copy image, and I'll paste it here, then over here. So this, what I'm gonna mark are your errors. I need to be, this is your error, this is your error, this is your error,
Okay, okay.
this is your error, 1 second, this is your error, and lastly, this is your error.
Mhm.
This term over here in the corner represents your error function. Okay.
Okay, so this is a function of yi means for a particular suppose a
What your data
point.
point is, yes. And if yi is what your data point actually is, y coordinate of your data
Mhm.
point. Any data point
Mhm.
is so, and f of xi is what you calculate. So difference between yi
Okay.
and f of xi. Now, when we do a mean, there are two ways to interpret it. One is that you get it absolute error, and one is that you get a squared error. Now, if we move further from
Mhm.
absolute error and squared error, there is mean squared error and mean absolute error also, which is basically means that you
Okay.
have a number of points and you divide it by that number. M is the number of data points, and you divide the whole absolute error or squared error by M. Rest of the,
Okay. Okay.
so like we see over here, this is what we discussed a moment ago. M is the slope and B is the y-intercept, right?
Mhm.
Now, sum of squared errors is this. If we the way now, if we know the error function, we can do a differentiated try if it's an optimization problem, then this can be solved by taking the partial derivative of the error function with respect to w naught and w1. W naught and w1, because if we expand this sum of squared error functions into this form, f is fy is fy, y of f of xi is
Yi. Hmm.
yi is a data point. For any data point has two coordinates, x
Correct.
and
Yi
y.
is the data point and f of xi is yeah.
What we
Yeah, yeah, please,
calculate,
please.
and this looks like an equation of line where w1 looks like the slope and w naught looks like the constant, it being y-intercept. So
Mhm.
we have expanded in this form. Once you have the sum of squared error expanded in this form, what we do is we differentiate, take partial derivatives of it, use of error function with respect to w naught and w1. Now, if we take the
Mhm.
partial derivative of it, then and we set it to 0 also, and we have to set it to 0 also. So I have not.
Which one you are saying to take it, set it to zero? Okay, to solve it, you have taken this as an example, is
One
it?
second, yeah, I'd share the equations with you also.
This is
If
a
we,
differentiation you have taken, right?
yeah,
Differentiation of that.
differentiation of error function with respect to w
Mhm.
naught and w1. Now, if we
Mhm.
do a w naught, only one term will be left. For w naught, when we do the differentiation of the error function with respect to w naught, we would get 2n, I believe, 2n.
You have differentiated with respect to W0 and W1, right? Two
One second.
parameters.
One thing. Let me do it and tell you what will be left. I can later post it over here and you can refer it back. I'd share the link with you in chat.
Okay.
One second. And
Yeah, I got this part. Yeah,
you got this part?
regression theory. Yeah, no, not that part. This part I did not get. That where
Okay.
you were doing the differentiation part. No, the differentiation part it's not clear to me.
Okay, so differentiation, basically what happens if you differentiate uh, error function with respect to W naught, whichever term does not have the W naught will get cancelled, will become 0. So only thing that will be left will be, and when you differentiate W naught with respect to W naught, you get a 1. So summation of -1 n times means minus positive 2n. I need to make it sure. Then we set it to 0. Then if we set it to 0, then what do we get? W naught. If we
So
the
you have
equation will
made a
summarize.
matrix in the form of a matrix. You have put it, right?
Okay, sorry.
Like W0 and W1.
Okay, no, sorry. We have to differentiate this one, this equation. This is what it's already been differentiated. This is the differentiation. When we differentiate this equation number d dot 4, we get equations d dot 5. D dot 4, D dot 5 you're
Okay.
getting. So so when you differentiate d dot 4, you get d dot 5, and then we set it to 0. So this is a concept of mathematics that when you have to if you have an optimization problem and your function is in W naught, let's say, or maybe W, just W, then if you have a function in W and it's differentiable, then when you differentiate a function and set it to 0, you get a maxima or minima of that function.
Okay.
I hope you remember it.
Yeah. Engineering days. Yes.
Yeah. So this
That
is
engineering mathematics now.
yeah. So
But this main making it 0 is to find out the maximum and minimum of these two
minimum.
functions, right?
When we equate it to 0, when we to find the maximum and minimum. So error function, if we reduce the error function, that is the whole goal, to reduce the error function. So once we have got the equation for error function, we try to reduce it, and when we reduce the error function, we get the values. We get we would get some values for W naught and Wi. So what we get is for which values of W naught and W1 our error function goes to is minimum. We are trying to find those W1 and W naught for which our error function is minimum. So these are the two equations which we get in matrix form. If we expand it, matrix multiplication, if we expand it, this is matrix multiplication. N is multiplied by W naught, summation xi is multiplied by W1, and when we multiply these two terms with W naught and W1, we get summation yi. This is equation 1. And then when we multiply summation xi with W naught and summation xi square with W1, we equate it with summation of xi yi. This is equation 2. This is a example data plot kind of example, mathematical example that the book was referring to, and you can go through it in later point of time. But basically it has what it's trying to show. It's trying to predict the skin temperature. What it's trying to do is it's trying to fit some line to a set of data points, and it is trying to predict the skin temperature with respect to heat flux. Water skin temperature is equal to 33.17 minus 0.22 heat flux. So this is the ordinary least squares model for doing the linear regression, where you have two-dimensional data points. You have x, you have y, and you do all of that. And there are some conditions to there are some conditions that should be met by the data set before we use the linear regression. So if you want to check more about,
So you've referred Khan Academy, okay.
yeah, I have taken this picture from Khan Academy where linear conditions for
I know
inference.
that. I also read a couple of materials on the YouTube link mainly I have gone through.
YouTube, yeah, we can go. It depends upon you which suits you. But I thought that I'd just refer to this because this is a like verified source of information. So
Correct.
L,
No, this is a good thing. Yeah.
so L is linear. So when this is like a abbreviation that you can remember, mnemonic for remembering the conditions for inference. It's for linear regression. It's liner, LINER. L for linear, which means that the condition that the actual relationship in the population between x and y actually is a linear relationship. Independence. Next, I is for independence. Is that the both what we have x and y are independent, not x and y, x and y are not independent. What? One second. The next one is that we have seen before. We are talking about general conditions for inference. Okay, so individual observations are independent of each other. What it's trying to say is that you have taken these data points, let's say heat flux and temperature, heat flux and temperature. Then whatever data point you pick from this data set, be it 3.732 or 5.531, they are independent of each other. It means that whenever you take a data point, take a reading, it does not depend on future data points or past data points, because that kind of gives you a sequence if it's dependent in time frames. So they are not dependent on each other. Any data point you pick from this table or any of these tables, they are all independent of each other. This is the independence condition. Now normal condition is that this was asked to me in an interview to give you
Oh, is it?
yeah. So whenever
What did they
you,
ask?
so if you, let's say you say you know linear regression, so by that the person will assume that you might have no fair understanding of linear regression, but what about the conditions under which linear regression can be applied? If you know linear regression, that does not mean that you
Okay.
so what these are the conditions. Linear is the condition that there should be an actual relationship in the population. X and Y should be actually linear in order for you to apply linear regression. Then is the condition of independence that two data points should be independent of each other. Then is a normal condition.
Okay.
Normal condition is that the distribution of a data point around your line. We have a line here. So if we equation for normal curve, this is the equation where we have f of x is the probability density function, sigma is the mean, and
What is this formula? This is a normal distribution function formula, is it?
yes, this is a normal distribution function formula which gives you the f of x probability density function, and sigma is the standard deviation, mu is the mean.
Okay.
So it assumes this is one of the conditions in linear regression, that when you're drawing a line from between the data points, that let's say you are drawing some points. Now you have some points over here. Sorry, I think this is okay. Now these, you are passing through this region, and this is okay. This is something difficult. Now, if you want to interpret that, let's say your actual line was this, and somewhere down this line you have this is not exactly how y is there. You have to see it in this. You have to look at it in a from a different angle, in three-dimensional angle, x and y, and then this is the normal curve, like it's shown over here, right? I hope so. This is what you're trying to
It's
say.
a bell curve. Yeah.
So it's in three-dimensional. Two-dimensional has been expanded into three-dimensional, and then it says that data points are distributed around your line in normal, forming a bell curve. Then equal variance. Equal variance is that, suppose you have this curve. This you have you have this. Sorry. Equal variance is that, suppose you have x and y like that, and you have a line like that. Now, if you have a normal distribution of data points over here like this, it will have a sigma, it will have a mean, right? This normal curve.
Means
Now,
mean and mode, right?
mean
Sigma?
and sigma is standard deviation. I'd open this.
Standard deviation rate.
Yeah. Sigma is standard deviation and mu is mean. I'd put it in chat. 1 second.
No, fine. I got it.
Okay. So what we have over here is, if you have a line, now at this data point, you have the distribution of data points around the line is defined by mu, sigma and mu. Now this sigma and mu cannot change for the entire line. If sigma and mu changes, variance, what is variance? Variance is variance is the square of standard deviation. Variance of, I'd open the formula, relation between standard deviation and variance. STD, dev, and variance. So standard deviation is the spread of a group of number, and variance is measured by average degree to which each data point differs from the mean. But mathematically speaking, when you get the variance, you take an under root of it and you get the standard deviation. Arithmetic. So shall we move on to the next part, or I should show you?
I think for today it is fine. We will just say 1 minute.
Yeah. So what I was telling you, we have covered the theory part for linear regression. This is what I was talking about. Sigma is the standard deviation, and this what essentially you have under the square root function is your variance. So I take a picture of it, and because at times I have to keep a track of. And then the last part is this practice question. Can we solve? I'd put it over here. Y equals to m to the power c. Can we solve it using linear regression?
M to the power c.
X 1 second. It's not m to the power c. It's this x to the power m. Sorry.
X to the power m into c.
Yeah, x to the power m into c.
And just put it there. Yeah.
Okay.
Directly, I think you can put it here. Just copy and put it in pen.
Yeah. 1 second. Y equals to x.
Y equals to x to the power m plus m into c.
Yeah. This was also asked to me in an interview. Can we solve?
Okay.
Can we solve this using linear regression? Can you give it a try?
I think
Or shall I?
it is possible. It is possible.
Yes, it is possible. That is correct. The way to do
Hmm.
it, way to
Because
expand
y
it.
mx plus c is the intercept, right? The intercept will take as 0, but the
No, if you
other two.
if you take C as 0, that will make it entirely 0, because C is in multiplication with x and m, right?
Hmm.
So C is not 0. You have to expand it for using the logarithm. I'll show the solution over here. And
Oh, okay, okay.
so if you take log y and you take log
Hmm.
of x into m, so when you take the logarithms, it basically
Hmm.
multiplication goes into addition.
Yeah, yeah, addition. Yes, 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 yes.
And if you
Then
take,
that x to the power m will come in the forward. M dot log x plus log
yes,
c.
so it's log
Oh,
y.
okay, okay.
So
Log y. Okay, 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 okay. Yes, yes, yes. Got it. Got it. Got it. Got it. Now it is clear. Yeah.
so these are like some questions which I have seen. I'd walk you through the implementation. Shall we? What